Happy Wednesday, metalheads! I am here. I am Jeremy, Penguin on the internets, here with my teammate Dan, and we are going to today be talking about all of the new hotness in Tinkerbell. Yeah, I guess there's also the banners. The banners work.
The banners are working.
Depending on what service you're on, it would not be clickable. But if you're able to type tinkerbell.org, you can find the site. And then there was also Twitter and all the other places. Happy Wednesday, Dan.
Happy Wednesday too, Jeremy. How are things going?
Not bad at all. I may ride the mute button. It seems it's time for the lawn to be trimmed, and so I've got a little bit of a little bit of that happening. But otherwise good.
Fantastic timing. Well, thank you very much for having me on today. We have quite a bit to go through. I've set myself some quite ambitious challenges. So we're going to be kind of going over a lot of the things that we've added to Tinkerbell over the last couple of months. But whilst we're doing that, I have the ambitious task of deploying 4 different operating systems to a piece of bare metal during this call. During this webinar. We're going to build an operating system disk image as well, and we're also going to rebuild one of the new components inside of Tinkerbell, which allows us to do some of that provisioning. So some inspirational tasks, which hopefully I think should kind of highlight some of the things that I think are very interesting that we've added into Tinkerbell.
Sure enough. Did you want to start any of that baking now, or are we going to hit that as we go?
Am I okay to start sharing, and we'll kind of start stepping through this?
Absolutely. Give me a screen.
All right. So I'm going to be sharing my entire screen. So please feel free to yell at me if things are not big enough or too big. I have a couple of slides just to kind of keep me on track, and then I'll kind of keep hopping backwards and forwards between my bare metal thing and running Tinkerbell. So with that, this is really kind of all around introducing all of the new features that we've basically been working on, I guess, in the last quarter. We've kind of neatly wrapped all of this up in a new release, version 0.5. I'll kind of cover that in a little bit more detail, but the 0.5 really relates to the Sandbox release, which effectively is us cutting a release based upon stable components that make up Tinkerbell. So I'm kind of going to kick off. I think some of the things that we've done, some of the things that we've achieved. Are pretty fantastic. Some of the things that we seem to be able to do at the moment, I have never seen possible, or I've never seen anything, I guess, comparable on bare metal, especially in terms of some of the feeds, some of the speeds that we seem to be achieving in some of the things that we're doing. So, I mean, I really do think that we are really rocking bare metal at the moment. And it is my intention to use this image every time I do a presentation about Tinkerbell.
As well, you should. And
Thank you.
appreciate the credit giving. When you keep on saying we, I know this has been a huge amount of your work and then other team members, but I think we in this case is the Tinkerbell community at large too, though, right? It's no longer just an internal thing.
No, absolutely. So I mean, kind of this kind of falls into what have we learned? So, brief history lesson. Tinkerbell effectively comes from inside of what was Packet, now Equinix Metal. It is the provisioning engine that has powered Packet pretty much, I guess, since its inception. And it's basically the engine that when you go to Packet, now Equinix Metal, and selects I want some bare metal infrastructure, it has been these components that have delivered that service for you and given you at your request some bare metal infrastructure. And last year it was decided to give that technology to the community, to the open source community, and there's been a lot of lessons, I suppose. So kind of kicking things off, we learned a lot in terms of, I guess, taking something that was very tightly coupled to existing infrastructure, and kind of having to decouple a lot of that. So there's been kind of a lot of work that was required to a certain degree generalize Tinkerbell. It originally kind of came with, as I mentioned, a lot of tight coupling to Equinix Metal infrastructure, a lot of kind of references to internal device types, the t-shirt sizes of bare metal infrastructure and things like that. And then we focused on kind of sanitizing it, and then really helping and moving it into a more community-led project. So we've done kind of a lot of work to get more and more people involved. We've kind of opened up a lot of things. We've done a lot in terms of making it easy to use and things like that. And there's been kind of a couple of quick lessons that have kind of come out of that. Some of it have been sometimes great, what seemed great ideas, but ultimately haven't worked in the first iteration. I suppose, unfortunately, one of the big things that we really wanted to do in the last quarter was to implement an event system into Tinkerbell. The idea being that you don't keep asking Tinkerbell what's actually happening, how things are going. You can effectively plug into Tinkerbell and subscribe to what it's actually doing. So Tinkerbell will tell you when a machine's been provisioned and things like that. We did implement this, and it all seemed fine until we then started to implement some kind of real world or larger kind of deployments with Tinkerbell, and we realized we'd actually impeded the use of Tinkerbell by implementing this event system in some ways. So we've had to disable that for now, and we will revisit that because we think this event system is going to be very important, and will make life a lot easier, especially as people build on top of Tinkerbell for their different use cases. So there's been a lot of lessons learned, really, in terms of making this an easier to use project, taking it more community led, and implementing these good ideas, or as we thought, good ideas. And we've kind of gone around and improved this by implementing things like proposals processes, implementing more and more kind of stringent management of kind of what's added into Tinkerbell, and again, kind of improved a lot of the communication by the community Slack channels, the community meetings, all of those sorts of things.
And so events maybe in the future, but what things did work out?
Well, yeah. So that's what we're going to kick off with. I've selected kind of 10 things, which maybe too many, but we can kind of we'll go through them. But I have kind of 10 things that I think are quite interesting for end users. So the first thing that we're actually going to do before we kind of step through those is I'm just going to kind of quickly, we're going to use Tinkerbell, and we're going to quickly deploy our first operating system, just so you can kind of see what that looks like. And then we're going to start to break down what we're seeing in some of the new features. So I'll just quickly pop out of here, and we'll move this out of the way. So this window that we can see here, and please yell if things are too small. I'm having to share my entire desktop because I need a number of windows.
Would be useful if it was bigger, if that's
Okay.
possible, since you offered.
Well, so what we're looking at in the center of the window here is KVM. This is I'm connected directly to an Intel NUC, which is going to be my bare metal server. So what I'm going to do is we will pop to. You certainly won't be able to see that.
That needs to be much larger.
Yes. Here we go. So let me make this much bigger. And shrink this window down a little bit. Apologies for not being prepared enough for this. Right, so that should hopefully be big enough now. Inside this, so this is my deployment server that I have, which we will use to deploy operating systems with Tinkerbell. We can see here under the template names, there's a lot of different operating systems that we will now be able to deploy. And I'm going to kind of step through what they look like a little bit later on. But what I'm going to quickly do is, I've already deployed, as you can already see, we already have Windows 2019 deployed. I'm going to delete that workflow. So we'll quickly find that workflow and delete it.
What's a workflow?
Give me 1 second and I will tell you. And so a workflow effectively attaches it attaches a template to a piece of hardware, and I'll explain what this kind of all means in a second. But what I'll do is, before I do that, I'm going to reset my physical machine to basically boot from Tinkerbell. So in a second, we will see this machine power cycle. There we go. And that will basically start provisioning in the background. So we can leave that to provision. This window will keep resizing as things keep happening. So effectively what we're doing here is we're using a template that I put together earlier today. And that template will take care of deploying effectively the smallest Linux distribution that I could find, which is a Linux distribution called TinyCore. And that template will effectively take care of all of the steps that are required to provision that operating system to the bare metal, and we effectively tie that template to a piece of hardware. So we can see where I created this workflow. I've applied it to this particular device, and this hardware ID, this MAC address, is the MAC address of my NUC. So in the background, we can see here there's a number of things happening. Effectively, what's happened here is this is the provisioning process. It's going to be really hard for you to see, but it effectively took 42 seconds from power on to provision that operating system. Once it's finished provisioning, the template that I've applied is basically asks the machine to reboot. We can see Grub is now up and running, and I am now in TinyCore. I have, in 42 seconds, deployed a brand new operating system to this bare metal server, rebooted it, and we're now up and running in there. So that's all done. So this basically is a very quick introduction to kind of what it looks like and how you interact with it, and kind of a little bit what it looks like. I'm going to delve into some of these bits in a little bit more detail. So to do that, I'll just bring this back up again. So the first thing that I really want to talk about is changes. I don't know why there's a spelling mistake there. Under is spelled correctly. Under the hood. So these aren't kind of UX changes or anything like that. These are changes that we've actually made to some of the Tinkerbell code. And what's important really there is that some of the key things that we really wanted to implement were cleaner functionality to reboot once you've deployed an operating system to physical machines, or alternatively to KExec. Now, KExec is a bit of functionality that exists within the Linux kernel, and the KExec functionality basically allows us to, instead of rebooting, to basically jump to that new kernel that we've written to a block device, to the disk inside the server, and basically start that operating system. Now, why not reboot? And there's a good reason for this, and that's mainly that big enterprise hardware takes a long time to start. When you have hundreds of cores and terabytes of RAM and multitudes of disks and devices and things like that, there is an operation that typically takes place in a server called post, which is power and self-test. And it can take a long time to enumerate through all of those devices. So that's where KExec comes in quite useful. So we will pop back to our bare metal server, just so that we can kind of see what that looks like. So we'll move this slightly over here. I'm going to delete this workflow. Let's move this up a little bit. And I'm going to create a different workflow, and this workflow is going to use a Debian template. Now this, and I'll show the template in a second. Let me create this workflow. So let me just pop to the correct directory. So this is the workflow. This is the template, sorry, and we can see here that there's two actions that are going to take place. I'm going to go through what these actions actually look like in a little bit more detail as well later on. But the first action is called image to disk, and what that is actually going to do is it's going to pull this compressed raw image from the Tinkerbell web server. It will run it through a decompressor, and it will write the output directly to an NVMe device inside this server. Once this action is completed successfully, the next action is going to be KExec. And as I mentioned, KExec is that kernel exec functionality that exists inside a Linux kernel. And what it's effectively going to do is it will mount that block device. It will find that new kernel inside there, and it will pivot directly to it. So we can see this in action, and we can see how quick this is. We'll do a reset to Pixie, and this machine shall power cycle. Ding. And we'll see the same things happen again. So it will boot up to. It will say, "What's my config?" Keep resizing this window, even though it'll resize itself. And we're going to run a different template at this point. So we're going to write over that operating system that we already had. We're now deploying Debian to this bit of physical infrastructure, making use of that new functionality that we've implemented recently inside the Tink worker. So again, this is going to be very small, but effectively what's happening is our in-memory operating system is starting. This will take another 10 seconds or so.
And that workflow is a template matched with that MAC address, and so only that machine will get provisioned when it turns on. So you're not
Correct.
accidentally going to provision whatever happens to be using that server as DNS when
So a
DHCP,
workflow is the linking effectively of a piece of hardware to a template that's actually going to run on it. So there we go. That took 45 seconds to boot and write Debian to the block device. It's not going to reboot, so we won't see the BIOS screen. We will see in a couple more seconds that we have logged into Debian. So I don't know if you can see that, but that's the Debian prompt, and we can log in there. So we can see on big bare metal servers, we don't have to do that posting, just straight into that operating system. So that allows us to move very quickly. Continuing on. So those are some of the under the hood changes that we've made. We've started to work quite a lot on the UX of Tinkerbell. So when I say UX, I mean this in kind of, I guess, two areas really. One is kind of the UX or even the UI of the CLI. So Tinkerbell has a CLI which allows you to interact with it and get list workflows and create and delete and things like that. A lot of those subcommands at the moment aren't aren't standardized. So we've been doing a lot of work to kind of standardize those. There's still work to be done, but we are opting for the same verb structure across all of those subcommands, and the capability to like pipe templates directly into things, and generally kind of make things a little bit more sane. And we're kind of opting to follow patterns that we tend to see in things like kubectl or kubectl. If you opt for that naming, don't at me. I didn't anyway. So as I say, we're trying to kind of simplify and standardize how the CLI looks. And then the other kind of from a user experience perspective is the Sandbox. I'll talk about that a little bit later on, but that is effectively a nicer way of getting access to Tinkerbell. Which brings me nicely on to number 8, the Sandbox.
It's later on.
It's almost like I planned this. So yes, the Sandbox. This kind of comes from lessons learned. Originally, we kind of open sourced Tinkerbell, and it's a number of microservices that make up Tinkerbell as a whole. It was a little bit difficult to kind of get hold of and kind of hard to use. So we've kind of put quite a lot of effort into making it easier for you to have a single place to get all of those components. And also, as I mentioned at the beginning, to stamp a tested and proven release that is built from a number of components. So version 0.5 is built from a stamped and tested Tink server, a stamped and tested Boots, which does the DHCP and TFTP, stamped Heagle, which does the metadata service, and all of those sorts of things. So prior to that, there was a lot of things left pointing to latest, which is a bit of a no-no because people were saying this isn't working. Pardon me. They had completely different set of components that they grabbed at a point where we were working on things. So the Sandbox basically gives us a stamped working set of components that an end user can get and run. And we've simplified this quite well in that there's basically, you can go to the Sandbox repo on the Tinkerbell GitHub, get that repo and effectively give it a few bits of information that it needs in order to bring up your Tinkerbell environment, at which point you can just start provisioning. Some additional work that we've seen from the community is Kubernetes Tinkerbell Sandbox. So this is running Tinkerbell on top. This is running Tinkerbell atop Kubernetes. So if you have Kind or Docker for Mac or a Kubernetes cluster somewhere, you can effectively apply the manifest and have all of those components up and running. And one other thing that a colleague did recently was put together a Tinkerbell Vagrant box, which is all of those components on an operating system inside a Vagrant box, which is then on the Vagrant store, which kind of makes it much easier for you to go there, get that, start that with Vagrant, and have it all up and running for you to actually kind of make use of. So, kind of leading on from that UX perspective, making things kind of a lot easier to use. CapT. So this has been something that I've been very excited about for quite some time. I've been kind of exposed to, so CapT, before I begin, CapT is basically a cluster API provider. So before I start waxing lyrical about CapT, Cluster API is a project that is part of kind of the Kubernetes SIGs, the special interest groups, mainly part of cluster lifecycle. And the idea behind the cluster API is that over the years, there's been many different ways of installing Kubernetes, and these projects sometimes fall by the wayside, or sometimes incur technical debt and things like that, and try to do too many things. The idea behind Cluster API is effectively like a standardization, a strong coupling in that Cluster API will have a definition of what a cluster should look like. Its job is to pass that definition onto a cluster API provider for it then to provide the end results, the provisioning, as it were. So Cluster API already has a number of existing providers that exist today. Things like Cluster API, AWS, VMware, Azure, Google Cloud, DigitalOcean, blah, 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 blah. There's quite a few of them already. It's becoming quite an established project. And it's becoming the de facto way for a good standardization of getting Kubernetes clusters deployed. Now, I personally have done quite a lot of bare metal Kubernetes deployments in my time, and it's quite tough sometimes. There's a lot of memes about these sorts of things and whatnot, but it's kind of a manual process. There's a lot of things that would normally be involved in getting a bare metal Kubernetes cluster up and running. And I think the linking of Cluster API and Tinkerbell is going to simplify that. And one of the cool things in doing all of this is that this integration has actually led on to some of the other kind of cool new features that we've actually implemented into Tinkerbell. So namely, another project that exists inside the Cluster API project is a thing called Image Builder. The idea behind this is that not only will Cluster API define the standards for how a cluster is deployed, it also kind of defines a standard for what the operating system should look like that's actually deployed by Cluster API. Now, Image Builder builds operating system images for most of the major cloud vendors, so AWS with AMIs and et cetera, et cetera. It doesn't provide, or there isn't really a standard for bare metal machines in terms of how you would get those deployed. One thing that we can do is use a raw image, and a raw image effectively is a byte for byte copy of a physical disk, which becomes a problem when you have, I think some of the newer hard drives are 12 terabytes and things like that. If I was to make a copy of that raw disk, I'd have a 12 terabyte file somewhere. So one of the things that we've been looking at doing is how we can compress those raw images so that they don't occupy the same amount of space and things like that. We have submitted PRs upstream to the Image Builder project. So that same project that builds all of these images for all of the major cloud vendors now will build a Cluster API image that we can use for physical bare metal machines. And it's that image that Cluster API Tinkerbell will be using to provision those physical machines that will become a Kubernetes cluster. So not only are we going to do bare metal provisioning with Kubernetes, but we also managed to stay lockstep with what they are doing in the project as a whole, which up until now hasn't really been possible. People have needed to use things like Ansible and SSH execing and all of the fiddly bits that are normally required to bind a cluster together. We're going to stay lockstep as best we can with the upstream project, which I think is going to kind of give us great feature parity between what you can do on-prem, between what you can do in the cloud with the Cluster API project.
Very good. And there's still 6 more things?
Yes, yeah. Yeah, absolutely. And 2 more operating systems to deploy and 2 other things I'm going to build as well. Actions. As I quickly kind of showed you in a template is effectively the list of things that will take place as part of the provisioning process. That process is effectively uses a number of actions in order to do that. So what we originally found is that a lot of the actions, the community were generating a lot of actions that were duplicates of others and things like that. And they were, an action typically is a container image that the Tink worker will run on a remote host. A lot of shell scripts, some actions were quite large, a lot of duplication and things like that. So we kind of realized that it probably made sense to have standardized actions that were small, followed kind of that Unix, Linux philosophy of do one thing, do that one thing correctly. If you want to do other things, chain them together and things like that. So we put together, here we go. So there is a Tinkerbell repository called the Tinkerbell Hub. And the Tinkerbell Hub basically is a place for people to create actions and upload them for the community to make use of. And you can see here we've got 8 main actions at the moment. These are kind of the core actions that allow you to do kind of most kind of things that you would require in a deployment. Some of the main sorts of things we would tend to see are wipe a hard drive, partition a hard drive, create file systems, write files to that newly provisioned partition. There's a KExec action that we showed earlier, which allows us to do that. Some of the things that are kind of quite interesting are we have an action called slurp, which I don't know, I came up with that naming off the top of my head. But effectively what that allows us to do is that allows us to take an existing operating system from a provisioned server and slurp the contents of that block device and send that to a remote server and compress that on the fly. So however you provision servers, one way or another, we can build that operating system manually if you like, and we can then slurp that into a disk image, which we can then provision elsewhere. So, you know, I guess one of the things that I want people to take away from this is that there are a myriad of different ways of using Tinkerbell. The most common and the most one that I will be talking about is mainly operating system provisioning. However, these workflows and the actions that you create or you consume can be used to do a myriad of different things. Firmware
What's
updates.
the most random?
Well,
As when reading over your blog post today, there was like so many things can be done that are outside the box, and you're like, well, if you're opening the door there, like, give me 1 or 2 of the most random ones.
well, I mean, that's a good question. I mean, as I mentioned, the most common one is basically provisioning. All we're seeing is provisioning operating systems because that's where this originally comes from. But we are seeing people, you know, kind of do things like look at how they would do forensic analysis of a broken system, whether they could have a workflow with some intelligence in there, which attempts to fix a broken system or restart services or you know, do those sorts of things. Packaging up firmware updates for hardware vendors into an action. You know, you may have a Dell HBA action, which you then tie to a piece of hardware and reboot that machine over BMC. It will then pick that action up and update the firmware and things like that. So not only are we looking at kind of ops work for operating systems, we can start to consider the more kind of firmware-y and kind of more low-level sorts of stuff. But this is the thing: an action can do anything. It's a Docker container at the end of the day that you execute on. So, you know, you could write a template that is huge that does everything, all the way to provisioning an operating system, installing Nginx, installing static HTML, to basically giving you a full web server from start to finish. There are many crazy things that people could do, and I would love to hear more about them. You know, if people start implementing those sorts of things.
I have a question before we get rolling. Would DD Small expand on first boot Raspberry Pi SD card style not work versus compressing a full image?
Let me see. DD Small plus expand on first boot. Can you bring that up again?
Disappearing. Yeah.
Oh, okay. So yes, I think I understand what this question means. So and I'll touch on this. Well, I'll explain it now, I think. So typically, what we find is that if you look at kind of the cloud vendors, so the cloud operating system that are available, so things like Ubuntu 2004 and whatnot, they provide raw images of certain types. So provide cloud images of certain types, like a cloud image AMI and things like that. How that tends to work is that the disk that is provisioned is quite small, so they basically made it look like it's only ever going to provision on a 10 gig disk. What normally happens is once that has been written to the server, when it reboots, the first thing that cloud image does is it will run a bunch of cloud init tasks, and one of those is normally a thing called grow part. Oh, Jason's beat me to it. Basically, what grow part will do is it will look at the size of the physical disk that it's been provisioned to, and it will go, oh, this 20 gig partition could be a terabyte. I will take care of resizing that on the fly. So I'm going to kind of cover this as well. You can do the same with Windows as well, which is something that I'll kind of hopefully try and show in a second.
Sounds good.
Documentation. We have done, I like to think, a lot of work in documentation recently. We have updated we've added huge amounts of documentation to docs.tinkerbell.org, all around how you would create a basic action. So how you would write an action. This is an example for writing one in Bash that would sit within an Alpine container. That this simple example basically just creates a file on disk as an example and things like that. And then how you would use that in a workflow. I'll come back to that in a second. We detail kind of best practices around actions and things like that as well, how they should work and interact with physical hardware. A huge amount of documentation in how you would set up Tinkerbell in different environments. And then finally, a lot of documentation around deploying different operating systems. So we're still within two minds whether we'll have a place that hosts workflows, but the idea behind this documentation really is it provides a good starting point for a lot of people to get different operating systems deployed. So I'm hoping now with all of this additional documentation, we should start to kind of ease the barrier that people are kind of hitting when they are deploying Tinkerbell for the first time. So ArtifactHub.io, what is that? ArtifactHub.io is where is a marketplace. I'll make this bigger. It's kind of comparable to hub.docker.com and things like that, but it effectively allows us to have a kind of marketplace for all of those actions that exist. So if you were to create a new action in the Tinkerbell hub, it will be published here, and we can see if we click on the action image to disk, we basically get how you would use that action, what kind of each of the different commands mean and things like that, and what it does and things like that. So we now have like a single place for people to kind of peruse, and the idea being you can go there and I need to do this task or this task and this task as part of building my template. And this place gives kind of a nice way of kind of going through there and finding the actions that make sense for you. So Hook. What I'm going to quickly do first, because I still want to deploy 2 more operating systems whilst I'm doing this, is we're going to deploy Windows, which obviously is a slightly bigger operating system. So I'm going to delete the workflow that we used last for Debian. And we're going to deploy Windows. Let me get my template list up. We're going to deploy Windows 2019.
Now, the last time I tried this, it took 21 minutes and 45 seconds.
So we're using that template. It's going to be the Windows 2019 template. Let's kick that off, because this takes around 200 seconds or so, which I still don't think is too bad for a large image.
Not at all.
Okay, so we will leave this rebooting in the background, and we should see this pop up once it's finished provisioning in around 200 seconds. So what is Hook? As I mentioned, there are a number of components that make up Tinkerbell, with the Tink server, Hegel, boots, etc. One of the main components is a project called OC, and OC is the operating system that starts. If we see, it's quite small text, but OC would be the operating system that would be started here. We found that OC does fill in, it provides us with this functionality. However, we wanted to start adapting a lot more new functionality and adding new things in to make things a bit quicker. So we thought about different ways that we could build these in-memory operating systems, and it kind of became clear that there was a really good opportunity to make use of a thing called Linux Kit by Docker. Let me just find the right window. Okay, let's make this a little bit bigger. So this really provides us, there we go. This really provides us with a lot of functionality in making life a lot easier. So Linux Kit provides us with the capability of building a brand new Linux-based operating system, normally within the case of around a minute or so. As I mentioned, the problem with OC is that it's a very big operating system that is designed to provide functionality for all of Equinix Metal's infrastructure and things like that. We wanted to move away from that. We wanted something small and lightweight. So we can see how quick this actually is in that I built a new kernel. Oh, let me just actually find out what it's called. .bpf. So I added in a new kernel earlier with BPF support. I'm using Linux Kit now to basically build that entirely new operating system with that new kernel that has BPF support. So we can see here that Linux Kit is basically pulling together a number of containers that will effectively be our new operating system. This operating system being Hook. So it basically will use out my new kernel that I've compiled. It will also use 2 additional new containers that we've put together, which are probably going to be a bit too small. I'll try and make this a little bit bigger. We can see there. So these 2 that we've added here will basically put Docker inside our new operating system, which has already been created, and it will add in another thing called bootkit. And here is our new kernel and operating system. This makes it very quick for us to be able to make changes to this operating system. So with OZ, it took nearly an hour to build the OZ operating system, which we could then use on a remote system as we provisioned. This normally takes around 50 seconds or so. So as you saw there, I changed the kernel that we were using to a completely different kernel and rebuilt that Hook operating system to make use of. Some of the things that we can actually do, and I can open up the config to make that a little bit clearer, is, sorry, let's make this a little bit bigger. So not only could we change the kernel image that we're actually using, we could also make use of additional images in here that would provide functionality like metrics and monitoring, logging to remote systems. We could add in here an SSH image. And it would be the case of basically saying name SSH and then the name of the image that we want to make use of. And then within a minute or so, we now have that new operating system with SSH enabled in it. So it allows us to iterate very quickly. We can see here, I know it's quite small, as I keep saying, Hook has now finished deploying Windows to that disk. It's now going to reboot, and the reason it has to reboot is there's no KExec into Windows at this point. And that logo should look familiar. That's 3 operating systems so far. So we have written Windows directly to this bare metal server, and we're now booting into it. So We'll leave that to finish doing whatever it's doing in the background. And that is Windows deployed to a bare metal server. And that's making use of Hook. And as I mentioned, Hook allows us to move very quickly, add in new functionality, use new kernels very quickly, and things like that. Number two is a thing called Crocodile. So this is very new. I wasn't sure whether I was actually going to bring this up or not, but as I mentioned, we saw how the Kubernetes SIGs were doing it with their image builder project, and it occurred to me that there's a number of different ways we can go about having operating systems for Tinkerbell. We already have documentation around taking things like the images that Ubuntu provide, which are in a format called QCOW, which stands for QEMU, copy on write format, but turning those into images that we can make use of. And I kind of put together a proof of concept which allowed us to build those operating systems in a very kind of quick and easy way. So I'll kind of quickly show you what that looks like. We're done with this one. Here we go. So let me make this one much bigger. Right, so I'll just pop back a directory. So effectively, Crocodile is an image building project for operating system images for bare metal servers. Underlying, it uses HashiCorp's Packer and a bunch of other bits and bobs to make it kind of simpler. And to make it really as simple as possible, it does everything within a Docker container. So I haven't decided yet, but we haven't built a Docker image for people to use. There's a Docker file which allows an end user to basically do a Docker build. And what that Docker build will do is it will build you locally a Crocodile image that has QEMU installed in it. It has the latest version of Packer installed in it. It has a variety of other dependencies that are actually needed. And that will build you your local copy of the image builder project. Once you have that, it's a case then of doing a Docker run and passing some volume mounts in there so that you get the finished article. But effectively, if you just do a Docker run on the image that you've built, you'll see we've got the Crocodile from Peter Pan. Don't sue me. Crocodile follows on with the naming convention of Peter Pan and Tinkerbell and things like that. It will build a variety of different operating systems, ESXi, Ubuntu, all of the Windows server editions and things like that. It will take care of actually getting those ISOs for you as well. So if you want to build Windows 2016, it will go and pull the Windows ISO directly from downloads.microsoft.com. It will then do all of the steps to build you your operating system image. Windows takes around about 8 minutes to do a very fast image build. TinyCore takes a minute, but I mean, that's a super small operating system. ESXi takes about 6 minutes, and that will build you your operating system that you can then deploy. So the idea behind this really is that this is a good base for end users to build on top of. I don't think that it would be feasible for us to have and manage everybody's different operating system configurations. There are limitless possibilities for how and the sorts of things that you would like to, ways that you would like to configure your operating system to deploy. So we've been as vanilla as possible with all of these. Like, it's basically, here's Windows that boots from DHCP, username Tinkerbell, password Tinkerbell, make use of it. But I like to think that if, here's a good starting point, fork it, make your changes. That's for you to kind of make use of. But this again gives people a great base in order for them to build those images. So you can choose one of these images, or you can pass along the bits that you would need. And then if we go to the images folder, we can see in here, these are all of the compressed raw images that would be produced by the project. And We use the image to disk action quite a lot, especially for this type of deployments. And the image to disk, really, the deployment time basically is based upon how long it takes to stream the contents of this to a block device. And we try to make these images as small as possible to make it very quickly. As the question that was asked earlier, we can provision what looks like a small disk and then grow it afterwards to make it much quicker for provisioning time. We can do the same with Windows, etc. That kind of brings me on to my final deployment. We're going to deploy ESXi. So let me go back to here. How are we doing for time?
Not bad at all.
Not bad. Okay. I can kind of quickly show you the. If we look here, we can see here that this thinks it's a 20 gig disk, which it's clearly not. Where does disk? I can never remember where these things live inside here. If I can find it quickly enough, I can kind of show you what I'm talking about.
Oh, the world's worst Windows quiz.
Yeah, where do things live? Somewhere in here is the option to manage storage. Who knows?
Not even getting any rescue from the chat. And
I know.
Twitch. Let's play Windows.
Where are my people at? Anyway, if I can't find it, it's not the end of the world. Yeah, I don't know. If you can find it, there is the capability to manage partitions in here. And you can do this through things like PowerShell, etc. We can basically take care of growing that disk and taking care of all the remaining capacity. Oh, here we go, disk management.
Got it.
So here we can see we've only provisioned onto a small amount of it. Extend volume.
Sure enough.
All the way to the end, and we're now using the full amount of the storage. So, as I mentioned, we can automate that with PowerShell and things like that. So that's how you would do that. Oh, somebody answered the question, I think. All right, excellent. So last operating system. That's 4 operating systems in a short space of time. So we will delete our old workflow. I can type. Oops, I forgot delete. Right then, let's find ESXi, which is FC. Oh, is my history letting me down? Oh no, there it is. There we go. We'll create that new workflow. Now we will power cycle the machine one more time. And Crocodile has already built a provisioned ESXi install. So it doesn't need to go through any of the install steps. Again, it will boot up. Tinkerbell will push hook to the machine as it boots up. Let's make this bigger. So we'll see in a second, that's hook being loaded at the bottom of the screen now. So that has been sent to the server. The kernel is starting. And we now have thoroughly tiny text. In about 10 seconds or so, it should start streaming ESXi to disk. So here we go. There's the Linux kit whale. And what you can't really see here is the Docker container has actually started. That Docker container is the image to disk Docker container that is streaming ESXi directly to the NVMe drive in here. It's a 300 meg disk, so it shouldn't take more than 20 seconds or so. So once it's finished streaming that to disk, we will then reboot into that newly provisioned operating system. But I mean, I think it's amazing how quick we can do this. It's not the most exciting thing to look at, waiting for an action to actually finish. One of the things that we're looking at doing is providing better output for end users to actually see what's going on. So there's a number of different ways we can go about that. As mentioned, it could be that we add additional things into Hook. Yeah, we shall see. This is taking longer than it should do. Have I cursed myself?
Maybe it tripped over something. I see the machine is appropriately named too. That one's Mr. Smee.
Yes. So this is a Nook that lives in my basement that has KVM support. Oh dear, have I been let down? Well, I wonder if something has gone wrong on the network or not. Just 1 second, just so I've not been messing around with anything. Very strange. Okay. Well, we shall leave that to carry on and see whether it actually completes. Who knows what's happened there?
Yeah, we've got one more. We've got one more left.
Yes, there is. And finally, really, is community. So, yeah, I think kind of one of the key things that we've seen really has been a fantastic amount of input from the community. There's been kind of more and more people joining the community calls. There's suggestions and ideas that we're seeing. It's been fantastic. I've been, I'm in the community Slack channels all the time and things like that. There's been a number of people that have been wanting to ask questions and show things. And on opportunity, it's been, I've opened a Zoom session and things like that. And they've been showing me what they've been doing with Tinkerbell. Sometimes you don't always get that kind of that feedback and such. So it's been fantastic to kind of see that there has been, kind of all these crazy use cases, and in some cases, there's one person reached out to me, and it turned out that they were automating hundreds of servers with Tinkerbell in their private cloud environment that they were running. They hadn't mentioned that before then, so seeing this was, it was pretty breathtaking. It was pretty amazing, and it was kind of vindication to a certain degree that there's kind of an amazing kind of community that's starting to grow and starting to do all these sorts of things. So I think for me, that's probably one of the key things that I think has been really good over the last kind of couple of months as we've been taking Tinkerbell further.
Yeah.
So I think kind of we've done kind of an amazing amount of different things with Tinkerbell. We've implemented a myriad of new functionality, a load of new tooling for Tinkerbell that people might want to make use of and allow them kind of new functionality and things like that. So I suppose kind of really there's a number of things that we're looking at doing next. We want to add in a lot more operating systems to make it easier for people to have that base to build on top of. There's always going to be more documentation that's probably needed to give people a better starting point for them to get and understand and build on top of. There's additional work in Hook. Now that's interesting. So for some reason, deployment has ended. It took 320 seconds though. Anyway, we got there in the end. That's something for me to debug. Yep, ESXi. I don't know. That's weird. Got there in the end. But yes, so there's a number of new functionality I want to add into Hook. We're looking at upstream integration, so how we would plug more things into Tinkerbell and ongoing work in Cluster API. And yeah, we've only just kind of started. And if anything, I have a goal to make Tinkerbell faster and faster. I think there's still kind of a long way for us to go, and I think we can probably start to scratch off even more stalled time to get us to even faster deployment times on bare metal.
Excellent. Yeah, if you have questions, if you'd like to contribute, if you fancy Dan's shirt, the Tinkerbell.org is a great landing spot and a jump off for Twitter and YouTube and GitHub and the Slack, and you'll be able to find us in all of those.
Excellent.
Good for now.
Absolutely. Thank you very much for having me. Thank you very much, everybody who's been contributing and helping out with everything that's been happening in Tinkerbell. I hope that this has inspired you and given you some ideas for things that you would also like to do with Tinkerbell. And I look forward to hearing from you all in the future. Thank you.
Yeah, drop by. Let us know how you're using it. Until later.
Thank you, everyone.